The last example that we have to look at in terms of applications, in this case it's an application of the cross product, is the concept of torque. Now what the heck is torque? Well, torque is produced whenever a force causes an object to rotate about its axis. That's just what I've put right there. So instead of causing a displacement, causing the object to move from one position to another, a torque causes it to rotate around and stay in one spot and just change its orientation. Now the formula for torque is usually written like this. Torque is R cross F. This funny looking T here is the Greek letter tau. That's the symbol for torque. Okay. R here is, it's a displacement vector, but it's a radial displacement vector. So it's the distance from the axis of rotation out to where the force is applied. So it's displacement from axis of rotation to the force. And of course, F here is the force that is causing our rotation. Okay. And the classic example here is just using a wrench here to turn a nut that's being attached to a bolt here. Okay. The force that is being applied out here on the end of the handle of this wrench. So this guy here is pulling the wrench kind of towards us. Our axis of rotation is right here in the center of where this nut and bolt is. So between where the force is being applied out here and where this thing is rotating around, you have this displacement from one to the other. Okay? And the torque is given by the cross product of these two things. So if you take your fingers here and point in the direction from the axis out to where the force is being applied, so put them along the displacement vector, and then curl your fingers in the direction that the force is being applied, so in this case kind of out of the board, you get the direction of the torque. And in this case, the torque is pointing down. Okay? So we're turning this thing and pointing down. Okay? If the force was going in the opposite direction, let's say we were pushing on the wrench instead of pulling on it, the torque would be opposite. We'd put our fingers along here like this, point in the direction of force, and the torque would be pointing up. Okay? And this obeys the right-handed system. So this is where they get that convention about, which direction you turn things to get the screws to tighten and loosen, right? Lefty loosey, righty tighty. Screws obey the right-hand rule, just like everything else in physics. Okay? So if you pull one direction, you're applying one torque. It's going to cause this thing to tighten, go down. If you push the other way, you're turning towards the left. The torque is pointing up, and that's going to cause the whole thing to loosen. Okay? So that's the formulation involving the cross product. Of course, we can also write this in terms of the angles involved. So we can have that torque is equal to the magnitude of the displacement vector, or the r vector, times the force applied, times sine theta. Okay? Where theta there is just the angle between r and f. Sorry. Angle between r and f. Okay? And the direction, we usually just add in at the end. It goes in this direction. That's sort of, this is a normal vector. So it just tells us that this whole thing is perpendicular to both r and f. To r and f. Let's just try that over again. To r and f. And torque has units of Newton meters, N dot M, okay? Because our force is in newtons, and the distance from that R vector is measured in meters. Okay. The thing to remember about this angle between R and F is if we're talking about the angles between two vectors, how do these vectors have to be placed? Tail to tail. Okay. So let's take a look at an example here. A bicycle pedal is pushed forward by an 88 Newton force exerted as shown in the diagram here. We want to find the torque. We know that our formula here is torque, magnitude of R, magnitude of F, times the sine of the angle between our R and our F vector. Okay? And we know we're going to use this formulation because we're given magnitudes and we're given angles on the diagram. So we've got our force right here. This is our 88 newtons. And we're pushing here. What we need to figure out is where is the axis of rotation of this system? Okay? Where's this whole thing going to rotate about? Okay, so we're pushing on the pedal. Here we've got sort of the shaft here that connects the pedal to our sprocket. Where's this thing going to rotate about? Yeah, right down in here. So this, I'm just going to label that as O for our center, or our origin, or our axis of rotation. Because this is the point that this whole pedal is going to rotate about. Rotates about O. Okay? So now, our R vector is from the axis of rotation out to where this force is applied. So this is R right here. So we can fill in our magnitudes. The magnitude of R is 20 centimeters, or 0.2 meters. Okay, because we want everything in meters. The magnitude of our force is 88 newtons. What is going to be the angle between our two vectors here if we place them tail to tail? Let's see, we've got this 83 and this 13. So from here to here is going to be 96 degrees. Yeah, that makes sense, 96. Now, let's imagine taking this R vector and this F vector and placing them tail to tail. I think the easiest thing to do is imagine moving F down to here, like this. Okay. So what is this angle going to be down here? Well, let's see. It's going to be the same. It's going to be 96 degrees as well. Okay. So we just put in sine 96 degrees. Does it make sense that those two angles are the same? Because basically we've got, F here and F here are parallel, so we've got that little Z pattern in there. These become alternate angles. Okay. So we can punch this into our calculator here. We get 17.5 Newton meters. Okay. What's our direction going to be here? Yeah, we're going from R to F. You're using the wrong hand, though. Yeah, it's got to be right-handed rule. So we've got to, remember, it's R cross F. So we start along R, like this, and then we curl in the direction of F, which gets us our thumb pointing into the board here. So this is 17.5 Newton meters into the page. Okay. R cross F ends up going into the page like that. Okay. There'll be a lot of questions, I think, where you're not asked for the direction of the torque. You're simply asked for the magnitude of the torque, in which case you don't need to go about worrying about the cross product. Okay? I just asked for it in this situation because I like getting you guys to use the right-handed rule. I think it's fun. Okay? Any questions? All right.